let's look at some practical problems that involve differential equations. We have a tank, 30 litres of solution of chemicals in the water. Concentration of the chemicals reduced by, okay, it's one of these ones where we've got the tank, we're pouring water into it, and that obviously dilutes it. The tank contains X litres of chemical at time t after the dilution starts. Show that dx to t is equal to this. So dx was the amount of chemical. So we're saying the rate of change of the chemical in the tank would end up being that. So we've got to show this. So what do we know? I know every minute the volume of the tank is going to reduce by 1 litre. They told us that. So therefore, at any time t, the volume is going to be 30 minus t litres. So we know the volume. But at time t, that therefore tells me the fraction of chemical of that 30 minus t, remember it's always going to be x, so x out of 30 minus t, that's going to be our fraction of chemical in the solution. But they also told us that this solution is escaping at 2 litres per minute, so therefore the rate of flow of the chemical must be 2 times the amount, so x on 30 minus t. So we have our expression, dx to t is minus, because it's escaping, so it's reducing, 2x on 30 minus t. Now we've got that information, find the fraction of the original chemical still in the tank after 20 minutes. Well, I've just said that that original volume be V rather than 30. dx to t is minus 2x on 30 minus t. Separate out my variables and I'll get, I said initially it's V, we want to link x and 20, we want to know what x is at t equals 20. So I end up with, well, they're both log functions. Now, well, if I bring that 2 into here, by the log laws it becomes squared. 1/3 squared is 1/9. I get v over 9. After 20 minutes we've got 1/9 of the original chemical is left. So the population of foxes on the island is our standard logistic equation there, y times 1 minus y. Okay. At time equals 0, the population of foxes is estimated to be 1/4 of the island's carrying capacity. And remember we said the carrying capacity was the higher of those trivial solutions. And we can look at this and we know the trivial solutions for this one would be 0 and 1. So therefore we know that the population would be 1/4 of 1, which is 1/4. Using substitution, y equals 1 minus w, we're going to transform that logistic equation to something simpler. It's simply going to be dw dt is equal to negative w, which is our standard exponential growth and decay. Well, remember exponential growth and decay was p to t is equal to a constant times p. So in this case our constant's -1. That's good, because if we can get it to that, we know the answer to that straight away, because we know that's going to be, ae to the kt, a is the initial population. We don't have to worry about integration, we can just go bang, there's the answer. So I guess that's why we want to transform it to something simple like that. It will save us a lot of time later on. Let's do it. Alright, the substitution is y equals 1 on 1 minus w. I'm going to need to work out dy to t, so I differentiate 1 on 1 minus w, there it is. But then that will be times dw to t, and that's what we're trying to find. But dy to t, they told me that was y 1 minus y. So putting that all together, I get everything now in terms of w. I've just got to make dw to t the subject of this. And nicely it does come out to be minus w. I've got a much simpler differential equation to handle there. So using that solution, find the solution of the logistic equation for y satisfying our initial conditions. Remember the initial conditions, we worked out y was equal to 1/4. It was 1/4 of the carrying capacity. So 1/4, let's now get that in terms of a w. And we said y was equal to 1 on 1 minus w. W then would equal -3 when t equals 0. There's our differential equation. We know the answer to it. So we got w is equal to -3 e to the minus t. Remember, it's just that a e to the kt. A was the initial population. We just said that was -3. E to the k in our one is -1. Now I can substitute back in Well, that tells me then that y, because remember y was 1 on 1 minus w, so y is going to be 1 on 1 plus 3e to the negative 2. How long will it take for the population to reach 3/4 of the carrying capacity? It's just an equation to solve now. So when is that equal to 3/4? Well, let's solve that exponential equation. Playing around with the numbers, eventually we get there. T will be the log of 9, which is 2.19722 approximately. So around about 2.2 years it's going to take to reach that. A rumour, we love our rumours, is spreading amongst 1,000 students in a school. Well, I made it 1,000. Our school's got a bit more than 1,000, but it makes it nicer for the mass, we just say 1,000. At a rate proportional to those that have heard it, and also those who have not heard it, which would be 1,000 minus x. As time progresses, people care less about the rumour. Well, yeah, that's true. In other words, what we're saying is the proportion rate is not constant. So here's the formula for our rate of rumour. It's our logistic equation with a little bit more involved this time. Kx, 1,000 minus x over t plus 1. Now, if initially one student starts spreading the rumour, which is how all good rumours begin, and after 1 hour, 50 students have heard that rumour. How many students have heard the rumour after 3 hours? There's our differential equation. Separate out our variables. We're saying initially, when t equals 0, only one person knows the rumour, the person who started the rumour. We want to know some things. Well, before I can find my answer, I need to work out what k is. I have another piece of information I can use to work out k, because we said after 1 hour, 50 students have heard the rumour. So we should now be able to work out k. Okay, let's play around with it. With the right hand side, that's just a nice log function, so I've done that straight away. Left hand side, I've played around with it with a bit of partial fractions. We can turn that into 1 on x plus 1 on 1,000 minus x, which again becomes a log function. But let's pull that together. There's k. What a beautiful expression. The log of 999 over 19 all over 1,000 log 2. Let's now work out what x is. So the same integral, but now I'm saying, well, when t is equal to 3, what is x? I'm not going to write all that down for k, I'll just leave it as k. We know, right, that's the value for k over there. So let's do, well, it's the same integration. I now get that the log of 999x on 1,000 minus x is equal to some constant value. Now, that constant value, if I do the calculation, is going to be 1,000k, k is what we just worked out over here, times, subbing into that, I'll get the log of 4. So that's 2 log 999 on 19. All right, we now know what our constant here is. All right, let's find x. Well, again, I've got log. If I bring that 2 in, it'll be 999 on 19 squared. So therefore, that's what 999x on 1,000 minus x is equal to. Algebra, playing around with that. There's x, putting it into our calculator, 734.558 roundabout. So after 3 hours, 734 students have heard the rumour. The lesson we learned from that is don't start rumours, because look how quickly they spread. After 3 hours, almost 3/4 of the school has heard this rumour. So 13A, some more differential equations to go and solve.